Good morning. I'm the acting commander, Josh Rudd, for the U.S. Army Corps of Engineers St. Paul District. I'll be the presiding officer for this public hearing. I am joined by members of the Corps Regulatory Division. Today's public hearing supports the Corps Section 404 Clean Water Act decision-making for the proposed Enbridge Line 5 Wisconsin segment relocation project. The hearing is specifically related to Section 401A2 the Clean Water Act, and whether discharges from the proposed project would or would not violate the Bad River Band of Lake Superior Chippewa Band's water quality requirements, and if conditions are available and necessary to ensure compliance. This hearing is being conducted in response to an objection from the band under Section 401A2 process, during which they requested a hearing. The band is a federally recognized tribe and sovereign nation, and the reservation's waters are downstream of project discharges proposed for Corps authorization. Today begins session 1, where I'll receive verbal statements from the U.S. Army, from the U.S. Environmental Protection Agency, Enbridge Energy, and the band. Tomorrow, session 1 will end after the Bad River Band concludes their verbal statements at noon Central Time. Session 2 begins at 1 p.m. on May 14th, and the remaining time will be allotted to receive verbal statements from the public. Please note the ground rules and agenda for this hearing, which will be visually posted periodically. At this time, I'm going to welcome Ms. Tara Fong, Director of the Water Division of the U.S. Environmental Protection Agency Region 5. Ms. Fong will provide EPA's evaluation and recommendations with respect to the band's objections.
Ms. Fong has not yet joined the meeting, so we should move on to the next speaker.
I am in the room. Hopefully you can hear me.
Yes, it's perfect. I'm so welcome.
Well, great. Well, good morning, everyone. My name is Tara Fong. I am the Director of the Water Division at EPA's Region 5 in Chicago, and I'm pleased to be with you this morning to present an overview of our 401A2 evaluation and recommendations on the Bad River Band of Lake Superior Chippewa's objection to the issuance of the Enbridge Line 5 reroute permit. I'd like to thank the Corps for the opportunity to join this morning and for organizing the hearing, and I look forward to hearing the rest of the discussion today as well. So in accordance with Section 401A2 of the Clean Water Act, EPA has submitted to the Corps a document entitled the Clean Water Act Section 401A2 Evaluation and Recommendations with respect to the Bad River Band of Lake Superior Chippewa's objection to the Enbridge Energy Wisconsin Line 5 relocation project. Today I'll present an overview of that document, and we encourage anyone who is interested to read the full document that we submitted to the Corps yesterday to understand the full context of our evaluation. I'd like to start by providing a bit of an overview of the neighboring jurisdiction process as outlined by Section 401A2 of the Clean Water Act. This begins on the left-hand side of the figure here, when a federal agency, in this case the Corps, receives an application and a certification or waiver from a jurisdiction. In November, the state of Wisconsin provided its 401 certification regarding the project to the Corps, which initiated a 5-day process for them to notify EPA of that receipt, which they did. That started a 30-day period for EPA to determine whether discharges from a proposed project may affect the water quality of a neighboring jurisdiction, in this case, the Bad River Band of Lake Superior Chippewa, and we made such a may affect determination in December. This started then a 60-day process for the Bad River Band of Lake Superior Chippewa to determine whether discharges from the project will affect its water quality so as to violate any water quality requirements. They did so in February and objected to the issuance of the permit and requested the public hearing that the Corps is hosting today. The Corps will collect information heard here and make its permitting decision. So we are focused today on the proposed reroute around the Bad River Band Reservation. It is a 41-mile reroute of the Line 5 pipeline with projected impacts to include 101 acres of temporary impacts to 534 wetlands, 0.2 acres of temporary impacts to water bodies, including 72 jurisdictional crossings, and 0.02 acres of permanent impacts to wetlands. Proposed discharges from the project to waters of the U.S. include construction matting placement to access construction areas, trenching to install the pipeline, blasting where hard rock complicates excavation, and horizontal and directional drilling and direct drilling to facilitate placement of the pipeline below water bodies to avoid surface disturbances. I will now turn to an overview of the ban's objection. The ban's objection raised concerns with discharges of primarily 4 types of activities, the ones on the previous slide. These include concerns regarding construction matting, including increased stormwater discharges, discharge rates, runoff, sedimentation, and thus increased turbidity, introduction and transportation of invasive species, and temporary impacts lasting longer than planned. With regard to trenching, the ban's objection raised concerns for discharges for soil destabilization, sediment discharges, and pollutant transport, soil compaction and mixing, leading to discharges resulting in altered soil water holding capacity, hydrology, groundwater processes, soil and sediment chemistry, and invertebrate and wetland plant habitat, and possibly the release of mercury and methyl mercury. The objection also raised trenching concerns regarding removal of vegetation from water courses crossed by open trenching that would result in impacts lasting longer than temporary or that will not be restored to pre-construction conditions. The ban's objection included discharge concerns with respect to blasting, including the effect of blasting residue on water quality and the contribution of pollutant loadings to water bodies, specifically nitrates, fuel oil, perchlorate, mercury, and other chemicals. Substances such as PFOA and PFOS, radionuclides, asbestos, arsenic, sulfur, and nitrates that may be discharged during the blasting process, and altered groundwater flow paths, groundwater levels, and groundwater surface water interactions, including changes in surface water temperatures. The objection raised discharge concerns regarding horizontal directional drilling and direct drilling, including the permanent conversion of wetlands due to establishment of a permanent maintenance corridor, increased turbidity and impacts to microinvertebrate communities and fish spawning beds, including lake sturgeon, and the inadvertent release of drilling fluids, and an introduction of sources of bioaccumulative chemicals of concern, including but not limited to PFAS and mercury, and also altered groundwater flow paths, groundwater levels, and groundwater surface water interactions. The ban's objection raised key issues, including that conditions in Wisconsin's permit and 401 certification will not ensure that the ban's water quality standards and other water quality requirements will be met for regulated activities that discharge to waters located upstream or adjacent to surface water. The objection said the project will result in non-compliance with the ban's anti-degradation provisions and the criteria, both narrative and numeric, derived to project designated uses and existing uses of the surface waters within reservation boundaries, and will cause or contribute to lowering the water quality below minimum conditions necessary to support designated and existing uses of the reservation's waters and waters hydrologically connected to those waters. So I will turn next to an overview of our evaluation process. Under Section 401A2 of the Clean Water Act, EPA interprets our role as an objective and neutral evaluator, providing recommendations to the Corps based on expert technical analysis of the objection and other relevant information. And we presented the full document for our evaluation and recommendations to the Corps, and are presenting an overview of that here as directed by the Clean Water Act Section 401A2, that at such a hearing, EPA will present recommendations with respect to any objection. We considered a wealth of information in our analysis, including documents from the Bad River Band and Enbridge, documents from the Corps and EPA, and from the Wisconsin Department of Natural Resources. Many of these documents have extensive appendices and addendums and updates, and this includes all of those. So this is, well, it might appear to be a short list, a wealth of information that we considered. EPA also received new documents and data provided by the Bad River Band on May 6th, last week. Receipt of this information with short order before today's hearing did not allow sufficient time to conduct a thorough evaluation of it, particularly the technical memorandum, evaluation and impacts of Line 5 Wisconsin Relocation Project on hydrology and water quality at the Bad River Band's reservation. We did not have sufficient time before this hearing to analyze, draw conclusions, or form recommendations from this new information. So accordingly, our conclusions are based on the analysis of information on the previous slide. In short, for our evaluation, neither the information provided by the band in support of its objection letter, nor the information contained in other documents reviewed by EPA demonstrated that charges from the project in any of the 4 categories, including pollutants in such discharges, will reach the band's waters in amounts that will result in a violation of the band's water quality requirements. The new information that we received last week, we have shared with the Corps for its consideration in its future permitting decision. For some more details on our evaluation, the objection cited 2 modeling efforts by the band's consultants. However, neither the modeling report nor details regarding the data and methods were provided. The objection asserted certain discharges will alter groundwater flow paths and groundwater surface water interactions. However, data, studies, modeling, or other analysis of these complex interactions at specific sites or how the discharges would adversely affect the hydrology of aquatic resources were not provided. And the objection cited general articles, scientific studies, and case studies. However, none of them substantiated the band's assertions about pollutants in discharges associated with the specific project reaching the band's waters. The materials EPA reviewed did not provide data, studies, or modeling analysis that showed and quantified impacts of distance, from any given discharge point to water quality on the reservation. The likelihood of discharges, including discharges of pollutants traveling from groundwater to surface waters and then to the reservation boundary. Predict quantities of pollutants in Enbridge's discharges or receiving waters. Compare the predicted changes in pollutant levels due to discharges against background conditions and natural variability. Evaluate the potential influences of other impacts on the landscape in water quality and quantity, or demonstrate how impacts from the discharges, including pollutant amounts, would adversely affect water quality in the band's waters so as to violate its water quality requirements. The only documents in the materials EPA reviewed that specifically addressed whether pollutants in discharges will reach the band's waters was a sediment discharge modeling report prepared by a consultant for Enbridge, showing that sediment discharges associated with the project will not have a discernible impact on water quality at the band's reservation boundary. EPA also evaluated Wisconsin's 401 certification conditions, and any Clean Water Act Section 404 permit, if issued, must include conditions from Wisconsin's certification, which included conditions for addressing all 4 discharge types. Many of those conditions minimize the risks that discharges will adversely affect the quality of the band's waters, including best management practices for erosion control measures to reduce sediment transport, inspection and maintenance requirements for best management practices, construction matting and access roads, crossing waterways and wetlands, preventative measures to avoid the spread of invasive species, continuous monitoring for signs of inadvertent releases, and restoration requirements for disturbed areas. It also included post-construction monitoring, including for hydrology, turbidity, macroinvertebrates, and other water quality parameters of concern, including mercury and PFAS, and implementation of corrective action when issues are identified both during construction and restoration. So in conclusion, following the analysis described, EPA concludes that neither the band's objection letter nor the other sources of information that we reviewed support the band's determination that discharges from the project will affect the quality of the band's waters so as to violate any water quality requirements. Therefore, EPA is not offering any recommendations under Section 401A2. EPA also provided the information that we received from the band to the Corps for its consideration in making its future permitting decision. Thank you for the opportunity to join you this morning. I look forward to hearing the rest of the discussion.
Song, I'll invite Enbridge Energy to provide their statements.
Screen. Yeah, you got it. Yeah, thank you very much. Should be. There we go. Thank you. Buttons figured out, Tim. What's that? You got the buttons figured out? Yeah, just, I think so. All right. Good morning. Thank you, everyone, for the opportunity to present on Enbridge's Line 5 Wisconsin segment relocation project. I'll refer to it as Line 5 or the project after this. My name is Joe McGaver, a manager environment projects with Enbridge. I have a chemical engineering degree. I'm a licensed professional engineer in Minnesota, and I've been working on similar pipeline routing, execution, and post-construction monitoring projects for the last 18 years. Next slide, Tim. I guess the important context of the experience is having the opportunity for continuous improvement, knowing how things have changed, knowing the actions required to incorporate in the project to get the end result everyone desires. Also presenting with me today will be Tim Drake, Ray Wulo, and Matt Horn. Before we get into the water quality specifics, next slide, Tim. Oh, can you go to the next one, Tim? Yeah, before we'll go back to that slide, but before getting into the project specifics, little general background on Line 5. Line 5 is critical energy infrastructure. It's a 30-mile pipeline that runs from Superior to Sarnia. It carries light crude oils and natural gas liquids, NGLs. The natural gas liquids are delivered to 3 propane fractionation facilities, one in Superior, one in Rapid River, and then also one in Sarnia. Then Line 5 also delivers to 10 refineries, as you can see on the map here. So Line 5 delivers products that everybody uses, whether it's fuels, and also used for many other items, such as to make clothing, factors in the farm, the food, delivering food to people, but also medical supplies and other equipment that people depend on. On the right-hand side of this slide, this shows Enbridge's pipeline system in the region. You can see heading south of Superior is line 61, 6A, and line 14. Those lines currently operate at capacity. They're full. Can't deliver more product, and also they're not designed to carry natural gas liquids. Line 5 is uniquely designed to carry natural gas liquids. Going from Griffith over to Sarnia, that's our line 78 pipeline. Line 78 can't receive additional volumes upstream, as I mentioned, and also line 78 is not designed to transport NGL. So when you look at line 5 and completing a project to remove the pipeline from the reservation and spend several $100,000 or several $100 million. That's why we would do it, because line 5 is the option to carry these products. Tim, if you could go back. Getting into the water quality piece, line 5 project has been designed to not have measurable impacts on the Bad River water quality. That will demonstrate through the presentation, through routing, project planning, design, and construction practices, the plans to monitor during post-construction, and then Ray will talk about surface and groundwater effects of the area, and Matt Horn will discuss modeling and other scientific analysis conducted. Next slide, Tim. As far as construction, the first thing we did was routing, looking at routes on a macro level. You can see we looked at several routes. Little variations aren't shown on here, but these main 4 routes show the areas considered, with the red line being RA01. The orange line is the proposed route. RA02 is the purple route, and then the green route is RA03, which is outside of the Bad River watershed. When looking at the routes, distance is usually the biggest factor or one of the biggest factors for impacts. All right.
Good with this, or
Yep, good with it. Oh no, go back to. Sorry about that. As you can see, the RA03 is a longer route and has more impacts to wetlands, water bodies, as well as forest and public lands. And that's RA03 would also have additional pump station requirements, valve requirements, electrical infrastructure to feed those pump stations and valves, which those weren't continued on further with the analysis due to the overall impacts. Go to the next slide. This slide shows the various impacts of the routes. RA03, as you can see here, was the highest in all categories. RA02 was the next longest route, which again, due to the length, had more impacts. When you look at RA01 in the proposed route, they're somewhat similar. RA01 has more forested wetland impacts, which is a feature to avoid, but also when you look at the proximity to the Bad River Band Reservation, the fact it crosses a state park, the proposed route was selected for the benefits of reduced forested wetland impacts, being further from the reservation and being able to use farmlands on that route that are already exist on the west side. Next slide, Tim. Once the proposed route was selected, a lot of routing, micro routing happened after that. That was done to avoid and minimize impacts to resources. So a lot of the routing we factored into crossing techniques, use of horizontal directional drill and direct pipe crossings to avoid water body wetland or impacts and also wetland impacts. Then we also looked at routing, like I mentioned, we looked at staying in open areas, farm fields on the west part of the project, looking at utility corridors, staying in those where possible, like along a power line, but also then in the remaining areas, looking at avoiding wetlands or crossing wetlands water bodies at the narrowest part of the crossing. And as you can see, like in this figure on the right, you can see where near neck downs, we neck down in wetlands. The right of way is reduced from 125 feet to 95 feet in wetlands, and also the routing efforts to avoid wetlands impacts. Next slide, Tim.
If I may interrupt, I'm so sorry. We have apparently people online are not seeing the slides advancing, but people in the current room can. Is there a way to make sure that the feed is also being what's shared on the virtual screen?
We're working on it right now. We have our experts at the computer trying to make sure we're sharing correctly.
Fantastic.
with the desktop instead of a screen. Again. Yeah. Slide 8, Jim.
I can move it forward. Did that resolve? All right, thank you.
The slide here covers the project overview. I mean, we did a lot of routing efforts. You can see the figures on the right show examples of crossings on the project that still exist. Lower right-hand corner is Bad River, which is an HDD crossing. Bay City Creek in the upper left, that's a perennial stream. Perennial streams flow all the time. Bad River is also a perennial stream that flows all the time. Bay City Creek would be crossed by a dry crossing, unnamed trib to Brunsweiler. That's an intermittent or ephemeral waterway. If it had water in it, which it doesn't in this photo, it would be crossed by a dry crossing, which will be covered later. And then unnamed trib to Potato is also a ephemeral or intermittent stream that would be crossed dry. But this gives you a range of the water bodies that exist on the project. When you look at wetland impacts after the routing, 0.02 acres of permanent wetland fill or wetland loss does occur on the project. That's roughly an area 30 feet by 30 feet. If you think of a small house, which when you look at a 41-mile project, that's a very small amount of fill. If you look at compared to a development building structure or parking lot can typically go well beyond that in some instances. And then when you look at the routing that we did to minimize and avoid wetland impacts, there is 101 acres of temporary wetland disturbance. It's not loss of wetlands, it's temporary, they would grow back. There is 33.9 acres of conversion from PFO or forested wetlands, shrub wetlands to emergent wetlands, and those conversion occur over our 50-foot easement in wetlands that we keep clear after construction, allowed to vegetate, but need to be clear for aerial inspection. As far as water bodies crossed, there's 204 water bodies within the project workspace. I mean, the project does have access roads, pipe yards, and valves, which are captured in that total to get to 204. You can see a large, or some number of wetlands are just crossed by access roads, not trenched through. Some are at valve sites, which aren't excavated through. You can see here the number that are crossed by HDDs. Next slide, Tim. More photos here. Upper left-hand corner is Bad River. Bad River, she will be crossed by HDD in the proposal. You can see on the upper right-hand side, that's a road ditch. A road ditch, which is an ephemeral or intermittent stream, would be turned to grass after restoration. Potato River is in the lower left, also a perennial stream that would be HDD'd, and lower right is another example of a ephemeral or intermittent stream that's only has water in it during portions of the year. You can see the breakdown of the different features on this slide between perennial and ephemeral or intermittent water bodies, with many of the larger perennial streams being crossed by HDDs. We do have some perennials that are open trench. There's 13 of them. And those are typically the smaller perennial streams on the project. And you can see there's 36 number of water bodies in our workspace that are crossed and would be controlled by erosion control devices to be discussed later. The Line 5 project will not impact Bad River's water quality standards. We designed the project for that to be the end result. We'll cover horizontal directional drilling, dry crossings, wetland crossings, and then other plans associated with the project to demonstrate that fact. HDDs So HDDs, we have 12 HDDs on the project, one direct pipe. Go through an extensive design process. We do the geotech to understand the substrate. Engineers then design the HDD. You can see in the upper right-hand corner, that's a typical HDD profile, where you have your exit and entry points, and due to the curvature of the pipe, the deepest part of the HDD almost always ends up under the feature you're trying to cross. So you can see in this case, the pipeline is like 70 feet below the water body. The lower right-hand figure, that's a hydrofracture pressure curve. And what that's done is it shows how the project's designed. The blue line is the soil confining factor. The red line is the anticipated drilling pressure. So when you take the blue line divided by the red, that tells you the safety factor. And you can see in this case, underneath the water body, the safety factor is well above 2. I mean, Enbridge, we don't want to have inadvertent returns as much as anybody, because of the impacts and then the extra effort to clean it up, and other social implications with having a release. You can see on the hydrofracture analysis, as you get to the exit and entry points, that's where the soil confining capacity gets lower, which if you look at the profile, that's because you're getting closer to the ground. So you have less soil to contribute to the confining factor. And that's why if you do see an IR, should they occur, it's usually on the exit and entry locations, because you're confining soils is getting less. Your safety factor does reduce there, but you're at the locations near the exit and entry where they're easily contained and can be addressed. There's been a lot of discussion that line 3 aquifer breaches were from HDDs on that project. That's not the case. Those aquifer breaches were from the use of sheet piling, which sheet piling is used to, it's basically driving, steel sheets into the ground. They go roughly twice the depth of the excavation. They're used to keep the trench minimized when you're or shoring up the excavation. If you have a deep excavation, that's what resulted in the breaches on line 3 was the sheet piling. When those went in, you pull them out, and then it left a channel for water to flow up, the artesian conditions to flow up. We did, as part of the design extra due diligence, we looked at the line 5 HDDs, and then compared those to the line 3 HDDs, and we went through that effort to check our designs, and we made a couple tweaks on a couple of the HDDs from what we found there to avoid IRs. So we've designed the project to not have IRs, safety factor, but also, I mean, you still need to prepare for the what if, right? We're out there working in the environment. So our HDD, we'll have specific training for the contractors prior to pullback. We'll have another review session with the team. We have equipment staged. We have IR response plans. The drilling operator, they monitor the drilling pressures to make sure they're not exceeding the pressure, which could overcome the soil confining pressure. We also monitor fluid returns. So if there's a loss of fluid returns, we would shut down the equipment. Do extra checking to make sure there's not an IR and resolve the issue should one occur. So we have staff that'll be walking the drill path to identify IRs. And like I said, we'll have equipment stage in the unlikely event that one does occur to clean it up as quickly as possible. A little bit on drilling fluids. Drilling fluids are actually 95% water. They have roughly 5% clay, a little bit less than that. And drilling additives are all from the Wisconsin DNR approved drilling list. And they're what's used in drilling water wells, and some of them actually are used as food additives in another application. Next slide, Tim. This slide shows dry crossing crossings, which if there's water present, like I said, we'll do the project for by dry crossing, which this allows us to minimize any sediment impacts to flowing water and also be able to install and restore the river crossing in a dry condition so we can see that we've returned it to the prior condition. The dry crossing for perennial streams will be surveyed by civil survey before and after to restore the river to its pre-construction contours. Don't want to go in this slide too much detail, but you can see the pumps would be started, dams installed, water would be pumped from between the dams, and then all the backfill and or excavation and backfill would be completed in a dry condition with making sure we're segregating the riverbed substrate in subsoil in separate piles and then returning them in reverse order. Next slide, Tim. Similar with wetland crossings, we've done minimization here. We've narrowed the construction right away to 95 feet. Wetlands will map the travel lane across wetlands to avoid impacts. As far as wetland excavation, topsoil will just be stripped over the ditch line. It'll be placed on a visual barrier, straw typically. Subsoil will be in a separate pile. The pipe will be installed, and then we'll backfill in the reverse condition in restore. We've learned over the years that to restore with have a slight amount of crowning to account for settling that occurs over the years ends up in the best result. And then we do have our post-construction monitoring to verify results that Tim will talk about later. And at this point, I'll turn it over to Tim for the next sections.
Good morning, folks. My name is Tim Drake. I'm a technical director of environmental inspection and compliance services within Environmental Resources Management Incorporated. I have both a bachelor's and master's degree in water resources, and I've been working on siting, permitting, construction, and restoration of linear projects for almost 30 years. As part of the project, Enbridge has developed project-specific erosion and sediment control plans. These plans incorporate best management practices to prevent erosion from occurring and to minimize the potential for sediment transport following a rain event or snow melt or from strong winds that could carry sediment into sensitive resource areas like water bodies and wetlands, potentially affecting water quality. These best management practices, or BMPs, follow the DNR's technical standards and include controls such as silt fence, straw bales, biologs, erosion control blankets, straw mulch, and other products used in different applications and at different times throughout construction and restoration. Once installed, erosion sediment controls are inspected and maintained until vegetation is reestablished following construction. The diagram here shows erosion control devices that were installed at a slope down to a water body that has been graded to allow for construction activities to occur in a safe manner to install that pipeline. This next slide shows the exact same area, but the erosion sediment controls have been replaced, reestablished to account for restoration of the original slopes and contours at the specific water body. These will all remain in place until successful revegetation has been established. Dewatering is part of the excavation process, or may be part of the excavation process, depending on groundwater inflow into the open excavation. It's needed to facilitate inspection of the excavation prior to installation of the pipeline to verify that the depth has been excavated to the right level, as well as that there's no obstructions in the ditch, such as a large rock that may damage the pipe or the pipe coating. Dewatering, similar to erosion controls, will also be conducted using best management practices and in accordance with permit conditions to prevent affecting water quality in adjacent wetlands and water bodies. Project has conducted extensive surveys to identify areas of shallow bedrock that will require the use of controlled explosives to fracture the bedrock and allow installation of the pipe to the desired depth. Blasting has been used for other applications by other projects, such as highway projects in the area. Top photograph here is actually areas that were blasted for the construction of Highway 13 just outside of Mellon, Wisconsin. Blasting of trench excavation is not like what you see in the movies where a building or a car blows up, or as it's used in open pit mining, but it's actually very highly controlled activity. It takes into account the type of material and the depth of fracturing that's needed. The amount of explosives used is kept to that minimum needed to achieve that fracturing of the rock within the trench line. Where blasting is needed to construct across a water body, temporary dams, as Joe has explained, are used to isolate the construction work zone from the water body and water body flow, pump that water around throughout the entire construction process. Ray will be talking more about blasting and groundwater in just a few minutes. Project has also completed extensive surveys for invasive species and has developed a project-specific plan to address invasive species. During our surveys, we identified over 23 different state-listed invasive species that were on the project within our construction footprint, plus one additional species, reed canary grass, which Enbridge was asked by the Wisconsin DNR to treat as an invasive species, even though it is not a state-listed species. The plan includes pre-treatment of the identified areas, as well as active equipment and personnel cleaning during construction. But it doesn't end there. Enbridge will continue to document the success of invasive species management throughout the construction process and will treat areas where weeds have been introduced or have expanded within the project workspace following construction. A project has also developed a very robust water quality monitoring plan that incorporates the collection of water quality samples from both wetlands and water bodies crossed by the project upstream and downstream of the proposed crossing location. Samples were collected in 2023 and 2024 across the project. Data from these samples were used in conjunction with data from other water quality studies conducted in the region to establish baseline water quality conditions and get a better understanding of what those existing water quality conditions are within the region. Samples will also be collected and analyzed during active construction and up to 5 years following completion of the construction of the project to monitor for potential changes that would potentially be attributed to pipeline construction for the project. In addition, the project has also developed a very robust post-construction wetland and water body restoration and monitoring plan that outlines specific restoration goals for establishing and reestablishing vegetation within this disturbed portion of the project right-of-way. Plan includes wetland monitoring for up to 15 years following construction in forested wetlands and replanting select tree species within the temporary workspace and forested wetlands to augment natural revegetation of trees that were cut during construction. Enbridge's revegetation plan will supplement the natural revegetation of areas disturbed during construction, reducing erosion potential and helping to restore the land to conditions similar to pre-construction. Finally, the project has purchased compensatory wetland credits from mitigation banks within the Lake Superior Mitigation Bank service area to offset permanent wetland impacts, including the 0.02 acre permanent wetland fill, the temporary disturbance to wetland habitat during active construction, and the conversion of forest habitat to emerge type wetland within the 50 wide operational right-of-way that will be maintained in non-woody vegetation to allow the aerial patrol of the right-of-way as well as the maintenance access for the project. Now I'd like to turn the presentation over to Ray Wulo.
Run the slides
If you want.
Yeah, that sounds great. Thank you, ladies and gentlemen. Thank you, Commander. My name is Ray Wulo. I'm a hydrogeologist with Barr Engineering Company. My degrees are in geological engineering, and for the past 40 years, I've lived and worked out of Minneapolis, and primarily my work area has been the glaciated terrains of the upper Great Lakes. Most recently, in the last 10 years, I've been involved in the Line 3 replacement project, primarily looking at after construction activities, a lot of monitoring. I was the primary hydrogeologist involved in controlling, working to control the uncontrolled artesian flows that we're going to talk about here. So I've had a tremendous amount of experience looking at the hydrogeology and the surface water hydrology of pipelines in the upper Great Lakes. Next slide, please. So what I'm going to focus on here is the hydrologic connectivity of the project with respect to the reservation. I'm going to focus on the construction activities and the post-construction activities, the hydrogeology and the surface hydrology associated with the construction area itself, and then those effects downstream as they would affect the reservation. The runoff is the primary concern evaluation in terms of surface water hydrology, but the runoff that hits the project has to first run overland and flow into the major streams, and the major streams are the connective component from the project to the reservation. Existing topography and other features such as roads and bridges are also a factor in that connectivity. In terms of groundwater, infiltration and recharge to the water table has been brought up as a concern, and also how groundwater flow would be affecting stream flow gains or lack thereof. And the areas of greatest groundwater contribution to the stream flow is actually downstream of the project. Most groundwater flow into streams actually occurs on the reservation itself. The hydraulic conductivity of the project to the reservation is indirect everywhere except in the immediate vicinity of the stream crossings. This picture here is taken from 2015 USGS groundwater surface water modeling project that was performed for the Bad River Indian Reservation. What this picture is depicting here is from their groundwater flow modeling, the stream and where the streams gain groundwater. What I want to focus on here is that red area there is where the highest amount of groundwater inflow into streams occurs, which is within the reservation itself. Outside of the reservation, there is some contribution to streams, but it's considerably less. And the project crosses those areas. The first thing I'd like to focus on is construction in terms of what I would consider to be a conventional trench excavation, which you use a backhoe to dig out the trench and then to lay the pipeline on. Excavation is nominally about 7 feet. It varies around topography, but that's typically what we're looking at in terms of this kind of a pipeline burial. The excavations are typically open for 72 hours, just long enough to put the pipeline in and verify that it meets requirements, and then backfill begins. As previously mentioned, topsoil and mineral soils are segregated. In most of the construction area, the topsoil is actually removed prior to construction occurring. In the trench itself, if there's any topsoil, that topsoil is laid out separately from the mineral soils below it. And then after the pipeline is put in place, the return of the backfill is identical so that the stratigraphy will be approximately the same as it was before construction. As Tim mentioned, there will be some low rate pumping of seepage water in some locations. In the upland areas, it's unlikely the groundwater will be encountered, but as you get closer to wetlands and streams, the water table in this part of the world is very shallow, and there will be some dewatering that takes place over a limited amount. And as Tim mentioned, just enough dewatering to be able to get the pipeline installed and verified.
Limited sheet piling will be used only where necessary. And I will talk a little bit about a very extensive evaluation that's been conducted to limit the amount of sheet piling. The reason we want to limit sheet piling is, as previously mentioned, on the Line 3 construction, sheet piling was the culprit for aquifer breaches. But as I'll discuss before here, the hydrologic setting is quite a bit different here, and we do not expect to encounter any artesian conditions in the construction. And then finally, best management practices are going to be used to minimize disturbance and control during the construction activities. Next slide, please. So in terms of dewatering, it's a short period of time. We're not using well points. We do the dewatering actually in the trench itself. We're basically evacuating water as the seepage occurs. This does cause a localized bit of drawdown of the water table. And when I say localized, I mean a few feet. And as drawdown is literally a few inches, except immediately adjacent to the slopes of the trench where you get a seepage face developing. But the drawdown is very limited. As soon as pumping stops, groundwater has an elastic response and it comes back. And that drawdown, that what we call the drawdown curve, it's a logarithmic curve. So it logarithmically is reduced to zero as you move away from the trench. The seepage that's being pumped out of that is going to be directed to various BMPs, bag filters as necessary to be able to take out any sediment, including colloidal material, before it's discharged to the ground. And the rate of seepage, of course, is going to be dependent on the permeability of soils. So normally, the groundwater is going to be returning back to its initial condition about a day after construction occurs. And in this localized event, there's going to be no effect on the reservation groundwater or surface water flows associated with dewatering. Next slide, please. The hydraulic impacts associated with the excavation are short term. As I mentioned before, there is a number of features that are being included to minimize sedimentation, actually to prevent it. The thing that strikes me about this project is each crossing and each construction has its own BMP designed for the particular topography and setting. So it's not a one size fits all. There's been a lot of thought put into making sure that sedimentation does not occur at the construction, including delineating the work areas and stabilizing the topsoil. So these impacts are going to be localized and they're going to be short term, a matter of days. Next slide, please. Now, trench blasting gets, I think there's a lot of confusion associated with it because people do think about these big explosions that occur, particularly associated with mines. Trench blasting couldn't be farther from that. It's a very specialized form of disaggregation of bedrock. The blast lines are staggered along the trench line along its center line. They only go to the depth of the target of the trench. The blasting takes place on the same day that the explosive is placed in each of the holes, and the blasting energy is directed upward. We call that relief. In many times people have tried to use explosives, for example, to enhance permeability for like wells, and it doesn't work at all. And the reason it doesn't work is because the confining forces of the rock, both sideways and up, prevent that blast energy from moving out into the trench. And so the material and the energy moves up. It's basically fluffing the rock, and then the excavator comes and removes that material. What's left is something that looks very similar to a trench. It's very controlled in size, and the fracturing is limited to within a few feet of the actual trench itself. I've seen trench blasting occur adjacent to condominiums, literally within half of a foot from a condominium foundation without any impact to the foundations. It's a very specialized type of blasting. And this blasting is not going to change the groundwater conditions. I think that people need to think about a blasted trench as being similar in almost every characteristic to an excavated trench. Next slide, please. So during blasting, the BMPs that are going to be employed will be similar to that they'll be used in regular trench excavation. One thing to understand is this type of explosive that's being used it's a packaged explosive in which it's sheathed in an impermeable material like a sausage. So it isn't poured down in the hole, which is what is done typically in mining conditions. These Explosives are designed for the size of the blast that's going to take place. They're put into the holes. The sleep time, the time that they're allowed to be in the hole where that explosive might be in contact with the water, is kept very small. What that means is that the leaching of any kind of nitrate materials from the explosive itself is essentially zero. And then when the trench blast occurs, there may be some residual, but generally speaking, these blasts are pretty complete. And Matt Horn will talk a little bit more about what the consequences or lack thereof would be about the residual nitrate in the blast. The last thing that I think there's a great misnomer is that the trench blasting is going to affect structures and wells. They do not do that. I have seen situations where local well owners have complained about a blast after the fact, and when you find out and you look in the well, what you find out is the well is old. It has a lot of crustation and material in it. It probably had problems with iron staining beforehand, but explosives in this condition are not going to affect wells, and the wells and structures are very, very far away from any of the blasting. Next slide, please. Once the trench, either a blasted trench or a excavated trench is constructed, in some locations there will be what is called trench breakers installed in the trench. They're essentially underground dams, and they're either a foam material that's sprayed in, or in the case on the right-hand picture, they're sandbags with an impermeable cover. And what they're designed to do is to prevent groundwater flow from moving along the backfill after it's returned back into the trench, and essentially preventing the excavation from acting as a French drain. Next slide, please. Here's an example of how this works at a wetland. On the top slide, we have a schematic cross-section of the wetland with the water table shown, and you can see the water table is right about at ground surface in a wetland, as in many cases it is. When the construction occurs, there will be a trench installed through the wetland and the pipeline placed, and then the backfill returned into the trench in the same order that it was removed, or actually reverse order, so that you have the mineral soils first around the pipe. If you didn't do anything else from that pipeline and its backfill could become a conduit for preferential flow that could cause some drawdown in the wetland. The way to prevent that, and this has been a very tried and true method, I've seen it many times in the upper Midwest in pipelines, is to install these trench breakers on either side of the wetland. What that does is that it makes the water level in the wetland equal all the way across, and two things happen. You don't get any drainage of the wetland. You also don't get any drainage and you don't get the development of any seeps down gradient of the wetland. In the last year and a half, I've done some monitoring up on line 3 at various locations where we've put in very discrete multi-level piezometers in and around trench breakers, and they are extremely effective at preventing groundwater flow from going across them. Next slide, please. Here's an example from this project of the proposed locations for trench breakers at mileposts between 4.4 and 4.9. What I want to draw your attention to are these red circles. Each one of those red circles is a location where a trench breaker has been planned to be placed. So you can see that there's over 10 trench breakers in this small area. They go along either side of wetlands. They go along either side of stream crossings where the slope of the topography is relatively steep. There'll be multiple trench breakers placed in there so that there wouldn't be gravity feeding down into those pipeline backfill material. The trench breakers prevent backfill from acting as a drain, and they maintain the groundwater at pre-construction conditions. Every segment along the proposed project has this kind of a plan where these trench breakers have been identified. Next slide, please. I think another misnomer that occurs with regard to pipelines and groundwater is that a pipeline, which is inert, acts as an underground dam that prevents groundwater from flowing across it. And nothing could be further from the truth. Groundwater flows slowly. Groundwater aquifers are thick. They're tens of feet thick or even more in most cases. And what happens is groundwater doesn't even see the pipeline. I've often used this analogy. A pipeline in groundwater is like putting a wire in a stream. the flow just doesn't see that. It just goes around it without any impact. I have never in my career seen a pipeline buried properly, that is not at the ground surface, act in any way as a dam. The excavated soils are going to be returned back in reverse order, and so the hydrology of the wetland and the functionality is going to be similar to what it was before construction. Next slide, please. Talk a little bit about artesian conditions, because they did gain notoriety in the Line 3 replacement project. And I just want to mention what an artesian condition is first before we talk about how this project is addressing that. An artesian condition is where groundwater is under pressure. It's under what we call confined conditions, and there is either a well or some other type of material penetrates into that, causing that pressurized water to not only rise above the confining layer, but actually rise to the ground surface. And that's the origin of flowing wells. And this is an example on the right-hand side of a flowing well, not as part of this project. And that's caused by the pressurization of groundwater. What we don't want to have happen is to have that pressurized groundwater breached, because it can cause the soils to lose its strength, and it's very difficult and expensive in some cases to stop that artesian flow. Next slide, please. So what have we done for this project as part of the artesian conditions? First of all, based on what we learned from Line 3, we went through an extensive screening process on this particular project, looking at the factors that might indicate where artesian conditions would be present. One are significant changes in topography, particularly along slopes of river valleys. Those are areas that we examine further. Also areas where there's high ground within 1 mile, where you could get the development of pressurized water that would be feeding a confined aquifer. Areas where there's wetlands or water bodies in the area that are elevated. The presence of fens. A fen is a groundwater fed wetland. They always are an indication that you have to look much further to see if there are artesian conditions. And then most importantly, there's been extensive geotechnical borings that have been performed along the site, as well as some available existing borings and wells. And each one of those along that route have been carefully examined to look for low permeability layers deposited over high permeability layers, which would indicate the potential for artesian conditions. Then the entire project was rated in terms of low, medium, and high for potential. We found that based on this information, there were no areas that had a high potential for artesian conditions. But for those areas that had medium potential, further geotechnical investigation was performed in the manner of doing drilling to confirm that there were not artesian conditions present along that. So based on this, we do not expect that there's going to be any artesian conditions encountered here. Also, the bedrock, the Frida sandstone, does not have artesian conditions in the shallow unit. At depth, we're talking 800 to 1,000 feet, there are artesian conditions, but in shallow Frida sandstone and some of the other bedrock units here, that just isn't something that's ever been known. Next slide, please. So some of the precautions that will be taken during construction, first of all, very limited use of sheet piling. Based on that geotechnical evaluation, we found that very few soils need to be stabilized with sheet piling. Why is that important? Because the Line 3 breaches, all of them involve sheet piling and installation driven to about 30 feet. And what happens is they breached a confining layer that wasn't known there. And then as they pulled out the sheets, or with the sheets still in there, we start to get preferential flow paths. And what you worry about is that high flow velocity along those flow paths causes piping of soil. And that's why artesian conditions are really of concern. But with a limited amount of sheet piling here and keeping the depth of the sheet piling to a lower depth, we're going to reduce the possibility further of encountering artesian conditions. We're not even expecting to find them. With blasting, I already talked about the fracture propagation is lateral, only for a couple of feet, and below the trench even less so. So our blasting is not going to cause the development of a preferential flow path in the bedrock. Next slide, please. So to summarize the impacts of groundwater, there's not going to be any impacts from dewatering of the trenches. The impacts from blasting are really zero. It's a localized effect, and it's done by and it's very controlled. Trench breakers are going to be used to prevent seepage from wetlands and the formation of French drains. The pipeline is not going to dam or otherwise impede groundwater flow or affect the hydrologic function of existing wetlands. And then artesian conditions are not expected on the project, and precautions will be taken during the entire construction to make sure that's not the case. That is the case. Excuse me. Next slide, please. So the impacts from stream crossing construction are the next topic. So as previously mentioned, horizontal directional drilling, or HDD crossings, are not going to have any impacts on stream flows. You drill underneath that at great depth. Dry crossings, that literally dry crossings that don't have any water in them, like ephemeral streams, there's not going to be any impact to stream flow, obviously. Trench crossings and dry crossings with flowing streams are going to be short-term. Typically, the damming process and the construction are less than 8 hours. In the morning, it starts. By the afternoon, the pipeline's put in place and it's over with. The use of the temporary dams, the biologs, et cetera, upstream and downstream, are going to prevent water from being in the construction area, and any dewatering that takes place is going to be routed through various BMPs to prevent downstream migration of sediment or increases in turbidity. Where there's really fine material, bag filters will be used, and if there's colloidal material or clay material, a flocculant will be placed in the bags to prevent that, because a flocculant basically takes really fine clay particles and it breaks down their van der Waals forces so that they can aggregate together and be large enough so they can be physically filtered out by the bag filters. And then turbidity will be monitored during construction and then extensively after construction. So stream flow, total suspended solids, and turbidity are not expected to be affected downstream of these constructions and won't be impacting across the reservation boundary. Next slide, please. Now we're going to focus a little bit on the hydrologic impacts of the cleared right-of-way. Primarily, this is what happens after construction's been completed. And I wanted to bring this up to put in perspective the amount of area that's going to be impacted. There's about 270,000 acres in the larger Bad River watershed. Of that, 144,000 acres are upstream of the reservation. Of that 144,000 acres, 118.4 acres of forest land will be converted to grassland, because the right-of-way has to be, by law, maintained to be opened and free from large shrubs. That's the law. So it's going to be converted to a managed grassland. What that amounts to is 0.04% of the total watershed of the 270,000 acres is going to be impacted. And if you just looked at those portions of the watershed that are upstream of the reservation, that's 0.08% of the portion of the watershed that would be affected. That's the water that feeds into the reservation. Next slide, please. So what are the effects of changing this 118 acres from forest to grassland in terms of hydrology? One is runoff rates. We express runoff in many ways, but one of the most common ways is looking at Manning's End, which is used to develop runoff coefficients. A higher Manning's End or roughness coefficient indicates more resistance to overland flow. So a deciduous forest would typically have a Manning's End of 1.5, whereas a grassland would be about half that, 0.8. What that means is that the runoff coefficient will be reduced by about 50%. What that will result in is a runoff rate, if you were to look at that for the aggregate of the project, of a reduction in runoff, or excuse me, an increase in runoff overall of 0.02 to 0.04% into the streams that feed the reservation. That's an unmeasurable difference. The other thing is these open grasslands, they will change the recharge rate to groundwater nominally. The differences in groundwater recharge rate between forest and grassland are very small. I'll give you an example. The USGS's modeling in 2015 for the Bad River Indian Reservation used a program called Soil Water Balance developed by the USGS. The SWB model uses different types of recharge coefficients for different types of materials. The recharge coefficient that is used in that model for both grasslands and for deciduous trees is almost identical. What that's telling you is that the difference in change in terms of how that affects recharge to groundwater is going to be too small to be measured at the reservation. The timing of snow melt is also an issue. When you have an open area, you would expect to get melting of the snowpack to occur earlier and over a shorter period of time. And indeed, a recent study that was conducted in Finland showed that snow melt in grasslands take about 40% less time to occur than snow melt in forest. So what does that mean for the project in terms of the hydrology? Let's take a look at the next slide, please. I'll talk you through this slide a little bit. This is for the 118.4 acres that are going to be converted. The plot here is a hydrograph, that is the flow in the stream as a function of time for the Marengo River just immediately upstream of where the project will be, so upstream of the reservation. And this is from 2024, and the period is March through May, so that's the snowmelt period. The orange line that you see here is the plotted actual data from the U.S. Geological Survey. So you can see that there's some peak runoff that occurs during snowmelt, and then it tapers off. Those little dark blue dots are the same flow that would occur if you were to compress that runoff from that 118.4 acres over a shorter period of time, and then have it earlier in the snowmelt season. You cannot possibly even here see a difference in flow, and that's not surprising because there's 50 to 100 CFS going through these rivers, and if the contribution from 118 acres is going to be extremely small and impossible to measure. The other thing is the runoff water at this temperature is going to be very close to freezing. So we're not talking about heated water running into the streams. We're talking about water that's very close to turning back into ice during the spring melt. Next slide, please. Concerns have been raised about mobilization of contaminants. Runoff controls during construction and revegetation are intended to prevent erosion and sediment transport. Many types of metals in particular, they don't move by themselves. They move as being on contact with sediment. So by controlling sediment, you control many of the things like arsenic, radionuclides, which, by the way, neither one is really present here. Radionuclides are not known to exist in the Freda sandstone in northern Wisconsin. The DNR has not identified this area as a location where soil and rock will have radionuclides of concern. Likewise, other metals such as arsenic are not known to be of a concern in this portion of Wisconsin. With respect to mercury and methylmercury, mercury is a unique metal in that it actually can volatilize at ambient temperature. So when you turn over some soil, you may get some mercury that has been deposited globally from coal-fired power plants and is everywhere and is ubiquitous in soil. You might get some mobilization back into the atmosphere of mercury. But the important thing to remember about this, the soils are only exposed for a brief amount of time. If they're exposed for a larger amount of time, the organic soils are covered, so that prevents them from oxidizing. And we don't expect that the conversion from forest to grassland is going to have any effect at all on terms of mercury concentration in water and runoff. And certainly you would not be able to detect any changes in mercury downstream at the reservation. PFAS, also referred to as forever chemicals, it's the contaminant du jour of the day. It's also atmospherically deposited globally. It's at very low concentrations in every soil. It's a worldwide phenomenon. It's poorly adhered to soil. This project is not expected to change that in any way at all because it's everywhere. Next slide, please. Invasive and noxious plant transport by water is also a concern because there are other ways, of course, to transport noxious weeds, the seed heads, and portions of the plant. Animals, of course, move that around all over the place. Wind moves that. But what we're focusing here on is how will this project, in terms of water, increase the transport of invasive and noxious plants. First of all, prior to construction, the noxious plant management plan that's going to be used is going to involve pre-treatment, so that there'll be pre-treatment along all the construction areas and to knock down existing invasive species. And then the BMPs that control sediment during and after construction are designed also to control the movement of those materials as they move through the water column. And then post-construction, and this I think is really interesting, is during post-construction, there'll be routine monitoring for the presence of noxious and invasive plants, and spot treatment is necessary for years on end after the construction is completed. The project's not going to increase the invasive and noxious weed transport to the reservation, and in all likelihood, because of this management process, is going to decrease the contribution. And you know, the bottom line is that the hydrology is not going to be the path in which that material is moved. So to summarize, I'd like to go through what I just talked about a little bit. There's not going to be any potential for violating the band's water quality standards on the basis of hydrologic connection, because the flow rates, the timing, and the temperature of surface water flowing into the reservation is not going to be affected by the project, either during construction or after construction. And that includes measurable changes in timing or temperature of water. Contaminants such as mercury, PFAS, et cetera, nitrates, they're not going to be increased in flowing waters into the reservation. And Matt, who's going to speak next, is going to talk a little bit more about nitrates as well. A groundwater flow and water quality entering the reservation or contributing to surface water flows into the reservation are not going to be impacted. Invasive and noxious plant transporting the reservation is going to be equal to or less than what's currently occurring out there. And the right-of-way maintenance and monitoring is going to ensure that there isn't going to be any cause for violations of the band's water quality standards during or after construction. You know, other conditions not associated with this project in the upper watershed all have a potential for impacting water quality. You know, things like climate change, logging, agriculture, road construction, maintenance, developments in the watershed, et cetera. They all are contributing to change. We live with change. Our object here is to make sure that this project is not contributing to that change. Thank you.
All right, good morning, everybody. I'm Matt Horn. I am a principal scientist and business unit lead at Tetra Tech, where I've been working for the last 15 years. You'll see that the reports authored previously by myself were authored by RPS. We were recently acquired about 2 years ago. Before that, I was with Applied Science Associates, who was acquired by RPS. Long career with one job and three different company names. I specialize in unmitigated and response mitigated trajectory fate and effects modeling of liquids, sediments, gases, and other substances that go into the environment. When I first began my career in about 2010, that was the time of Deepwater Horizon, the large oil spill in the Gulf of Mexico, where I was supporting the US government, specifically NOAA and the Department of Justice, to assess where those substances were moving, how they were behaving, and what those effects were in the environment. My company is uniquely positioned. We do about 50% of our work with government and about 50% of our work with industry. We're the impartial scientists that are currently operating in about 50 different countries. You may have seen my work previously. I've been working on this project specifically for about the last 4 years. I've conducted a number of assessments. One of the ones that I'm going to be referring to over the course of this morning is the construction assessment, where we actually conducted about 20 different modeling simulations of sediment dispersion within the watershed of the Bad River Reservation, looking at hypothetical concentration changes and what that would mean following construction activities. The reason I'm talking about that construction report is because we do anticipate that there are some potential changes to sediment in the water, specifically from construction activities, right? You're going to be trenching waterways, and there's the potential for an inadvertent return. I'm going to touch on various other water quality criteria like pH and DO and a number of other things to talk about the quantitative metrics. But what I first want to do is introduce you to a little bit of the narrative criteria that the Bad River Band has set forth. I've copied and pasted onto this slide. I'm not going to read through this by any stretch. The narrative criteria and general narrative criteria for water quality that the band has set forth. When you do read through this, there are a number of different concerns that are laid out, specifically in 6 different areas. The first concern is around pollutants. The second is on radioactivity. The third on water quantity and quality. The fourth on hydrology. The fifth on mineral changes, and the 6th on temperature. As it relates to pollutants, this is a construction-related project, right? This is excavation of waterways with the potential for an inadvertent return. Pollutants are going to be a very small portion of what I'm going to be talking about because there are not hazardous substances that are being introduced with this project. As Ray mentioned, radioactivity should not be a concern because the rock material that is contained in this area does not contain radionuclides. The excavators and other things that Enbridge would be constructing this project are also not radioactive, so this is not a concern. The project itself will not affect the water quantity. There is not additional water being brought in or water being removed by the construction activities. There are potential concerns around water quality, and I'm going to get to those specifically around total suspended solids within the water. As Ray has gone in depth, there should be no changes to the hydrology in the area, and there are many different methods that have been employed to ensure that the hydrology does not change. The rocks, the soils, and other things are going to be put back into place in the same stratigraphy, so there should be no mineral changes. And I'm going to talk a little bit more about specifically any potential change to temperature. The Bad River does also have water quality standards with specific numeric criteria. Those first ones were a little bit more loose. As it relates to specific criteria, there are numerical ones associated with dissolved oxygen, pH, bacteriological water quality, and turbidity. What I'm going to do is I'm going to walk through kind of from start to finish and lead with the ones that have minimal potential for effects and finish with the one that we've done extensive amount of modeling to talk about what those potential effects are going to be, specifically around turbidity and sediment disturbance. But very quickly, temperature has the potential to be affected in this area by tree clearing, which would remove trees adjacent to waterways, which would essentially reduce the amount of shading, so there's more light, which can warm the water. That temperature change can result in changes to dissolved oxygen throughout the waterway, where very specifically the Bad River Band has stipulated that daily minimum dissolved oxygen concentrations should be 5 milligrams per liter in all cases, or 6 or 8 for those cold water fisheries and those waters that might have the early life stages of cold water fish. For pH, very specifically, there should be no change greater than about 0.5 units over a period of 24 hours. You're going to notice that some of these criteria have a change based upon baseline. So this is 0.5 units from baseline, with the understanding that the baseline pH in many of these waterways actually changes themselves. So this accounts for additional change on top of that natural variability. For bacteriological water quality, the geometric mean should not be less than 5 samples, meaning you need to take multiple samples at a given location, and that over a 30-day period, E. coli should not have more than 126 CFUs or colony-forming units. E. coli is the bacteria that's contained in fecal matter from human waste, pet waste, and other animal waste, essentially poop. For total nitrogen, there are no numeric criteria set forth by the band, but what I'm going to be doing is talking a little bit more and taking it one step further. Ray talked about the nitrate contained in the low residue gelatin blasting. I'm going to talk about some conservative assessments that we've done to assess what the total concentration of nitrogen should be as a change from baseline based upon some conservative criteria. And then I'm going to spend a good deal of time on the turbidity. Very specifically, the Bad River Band has said that turbidity shall not exceed 5 NTU, that's Nephelon turbidity units, over background turbidity, when the background is 50 NTU or less, and that the turbidity shall not increase more than 10% when the background turbidity is more than 50. The reason that this regulation is set in place such that you essentially have a threshold at low values or a 10% at higher values is because turbidity varies a lot. And I'm going to get into a number of different relationships and very specifically talk a little bit more about turbidity being an understanding of how much sediment's in the water, versus the numeric criteria, which is set up around NTU, or Nephelon turbidity units, which is essentially how well does that water transmit light? What's the opacity? And they are not one-to-one relationships. So the Line 5 WSRP did investigate historic samples and other sampling in the area. I want to set the stage by talking about very specifically the natural background variability, and very specifically what the project's contributions should be to natural background. There are quite a lot of samples that have been collected throughout the watershed. Between 2010 and 2022, the Bad River, Wisconsin DNR, USGS, and Glyphwick have sampled these waterways extensively. There are over 17,000 measurements of temperature. There are almost 1,000 measurements of dissolved oxygen, pH, and total nitrogen. You're going to see there's a smaller number of samples with ammonia, but still 42, that's a good amount. And about 1,000 measurements of both TSS and NTU. And in many cases, those are co-located, which means that we can start to develop a relationship between TSS, the mass of rock, total suspended solids within the water body, as well as that measure of opacity with the NTU. Enbridge themselves have also gone out in 2023 and 2024, sampling maybe not as extensively, but over 500 samples of temperature, dissolved oxygen, pH, total nitrogen, ammonia, and then TSS and NTU. Enbridge has sampled over 204 different water bodies, 145 different wetlands, and monitored about 435 in total. In addition, I'm going to be calling to a little bit more data from the Meander Bank Stabilization Project that occurred later this winter, early spring, around the March timeframe in 2025. And the Meander Bank Stabilization Project has data that was collected at the Meander within the Bad River Reservation. So what I'm going to do over the next several slides is walk you through a combination of first an understanding of what the natural variability is, and then on the second slide in each one of these, I'm going to talk about the project's predicted change from natural variability. So each of these slides is going to be laid out the same. In the upper left-hand corner, we're going to be looking at the minimum values, the maximum values, and the average across that statistic historical data, which is going to be on the right-hand side shown in that light blue bar. All of the data from basically the Potato River at the bottom all the way up to the top of the White River is all of that historic sampling between 2010 and 2022 that was conducted. And we've got in that first column the number of values collected. Here we've got over 17,000 temperature samples. And then the data, either average value, minimum value, or maximum value for the next three columns, as well as the standard deviations. I'm providing all of this data to give you that understanding of just how much variability there is. When we're talking about the water temperature in this area, in northern central US, which has hot summers, has cold winters, that water does freeze, you do see annual fluctuations of about 50 degrees Fahrenheit in water temperature, and daily fluctuations in temperature can exceed 17 degrees Fahrenheit in just one 24-hour period, right? That's going to be really intense solar heating during the day, and then you get that clear cloudless night where you're going to get lots of cooling. Water temperature can vary extensively. When we look at the bottom two rows on each of these tables, you're going to see the Enbridge field sampling programs, and that's the 2023 and 2024. You're going to see the number of samples collected as well as the minimum and maximum values. And the things I'm going to try and call out are very specifically whether or not Enbridge field sampling aligns with some of that previous sampling. And in the case of temperature, the values were kind of spot on. They were in line with the historical. You're going to see maybe those minimum values aren't as low and those maximum values aren't as high. And that's just going to be because some of that Enbridge sampling did not take place over the course of the entire year. It was limited to non-winter conditions in some cases and some other limited seasonal conditions. So for temperature, remember we were talking about what are the potential impacts to temperature from this project, and we're really considering the removal of trees resulting in a loss of shade, which can then increase the solar insolation or the amount of sun hitting the water in those areas adjacent to the waterway. Ray has identified that about 0.04% of the watershed would be converted from forest lands to this grassland. And that's going to be a 50-foot right-of-way in which only a very small fraction of that is going to be adjacent to a waterway, right? If you were going to imagine yourself standing on the right-of-way next to a waterway, only a couple meters or tens of meters away from the bank are you going to have any sort of an impact on the amount of sun reaching the water. If you were at, and on the bottom right-hand corner, I'm gonna show you that meander, and that kind of gentle line moving through that meander is from east to west is the existing Line 5 pipeline. If you were to stand at that meander on the eastern bank, the only time that the sun could impact that waterway with a little bit more sun would be either in the early morning when the sun is in the east, or the late afternoon when the sun is in the west. If you think of moving around from east to south to west as the earth rotates, the solar insolation at noon when the sun is at the south is going to be just the same. If you were to then think about maybe if you were in the waterway on the southern edge of that meander where the water flow is coming from east to west, then the morning sun and the afternoon sun would have no change. And the only amount of increase in solar radiation would be during those noontime hours when the sun was at the south. Why am I walking through this long argument and discussion? Because what I'm trying to point out is that you have very small sections of these waterways, 9 to 15 meters of downstream distance, that have any potential to see increased solar radiation from tree clearing. And that is totally dependent on the time of day, year, weather, cloud cover, and orientation of the waterway. Wisconsin DNR did an analysis which looked at the maximum anticipated temperature change based upon as many conservative assumptions as they could, and understanding that rivers do flow and water is going to be moving through that area. They have predicted that there would be a change of about 0.018 degrees Fahrenheit maximally. So based upon this data, it's really impossible to conclude that there would be any measurable change in the waterway, and it would be impossible to think that there would be any change in temperature 2 kilometers downstream in the reservation, very specifically because when you look at a river like this on the right-hand side, and you understand that portions of that river are in sun, portions of river are in shade, you've got turbulent mixing throughout, I can tell you definitively that there are more than 0.018 degree Fahrenheit variations from bank to bank, vertically in the water column and throughout. All of the construction activities will take place more than 2 kilometers upstream of the reservation, and any temperature change associated with that would certainly be unmeasurable even just a few meters downstream, let alone within the reservation. In addition, there's cooler groundwater influx that happens in the reservation, as you saw from that image with the large red amount of groundwater infiltration into the reservation, and all the natural mixing and the downstream distance would make any temperature change short-lived and unmeasurable. When we think about dissolved oxygen, we have to have the understanding that dissolved oxygen is a measure of oxygen gas contained within the water. Actually, one of my PhD topics was about air-sea gas exchange and understanding how gases move between the water and the atmosphere and vice versa. Oxygen is driven into the water by concentration gradients, where oxygen in the atmosphere goes into the lower concentration waters. And if there is productivity in the water, say by primary producers like phytoplankton, and there's more oxygen in the water and it's supersaturated, that oxygen actually evades from the water entering the atmosphere. Natural variability in this system sees minimum concentrations of oxygen as low as 0.64 milligrams per liter and as high as 89.90 milligrams per liter. That is very supersaturated water. Oxygen would be evading that water. On average, the concentration is about 11.02 milligrams per liter throughout the reservation. And when Enbridge went out and sampled about 450 measurements throughout 2023 and 2024, they found concentrations. They did see some concentrations that were lower, about 0.64, and some very high concentrations at about 55. Why is this important? Because you do see some of those lower concentrations very specifically within wetlands and other water bodies that might have high organic content in low amounts of water turbulence and water flow. So that Enbridge field sampling is great, but it's not a one-to-one where you're seeing in the top, 3/4 of those tables, those are all moving waterways. And the Enbridge field sampling includes those perennial waterways, intermittent waterways, as well as some of those stagnant water bodies and wetlands. So as you've seen from those minimum and maximum values, and I've carried those through in the top right of each one of these, you can see that they're extremely variable throughout any given day. It's dependent upon the temperature, the atmospheric pressure, turbulence within the water, wind conditions, biological processes, respiration and decomposition. You do see a large amount of variability, and understanding that the numeric criteria state that concentrations need to be 5, 6, or 8, depending on the specific location and time of year. What we wanted to do is say, look, we do understand that the Line 5 construction activities do have the potential to impact very specifically temperature by about 0.018 degrees Fahrenheit, and we saw on that previous slide. And because oxygen saturation is dependent on the temperature of the water, when you see increases in temperature, the water's ability to hold oxygen is actually reduced. Warmer water holds less oxygen. So if you actually do see an increase in temperature, you see an increase in the oxygen saturation because it can hold less oxygen. If the water becomes supersaturated, oxygen evades from the water, and therefore the concentration in the water goes down at higher temperatures. When you look at that 0.018 degree Fahrenheit change, what that is associated with is a DO drop of about 0.01 milligrams per liter, or about a 0.09% change in saturation. So it's not possible to conclude that there would be any measurable change. This is actually below the detection limit of most sondes that would be out there, and certainly at or below the detection limit of the Winkler titration, which is used to calibrate and verify those oxygen measurements of the sondes. Again, remember that the construction activities would all take place about 2.1 kilometers upstream of the reservation, and because of that, it is impossible to conclude that there would be any kind of a measurable change in dissolved oxygen at the disturbance point, or certainly 2 kilometers downstream within the reservation boundary. Therefore, there would be no cause for ecological harm, no promotion of algal growth, or result in any measurable change to the water body in any way. pH is a measure of the acidity of the water. For those that remember back to high school chemistry, low numbers of pH, anything below 7 is considered acidic water. Anything above a value of 7 is considered basic water. Vinegars are things that are acid, sodium hydroxide, and detergents are things that are bases. The minimum values throughout the reservation have been measured to be about 3.49. That is acidic water. And that is water that's typically found within wetlands and fens and other stagnant waters that do have high organic loads and can result in increases in hydrogen ions in the water column. The maximum values are about 9.13, which is slightly basic water. Remember, pH is a logarithmic scale, which means that when you move away from 7, a value of 8 means there's 10 times more hydrogen ions. And when you move to a value of 9, there's again another 10-fold change. On average, pH within the watershed is about 7.68, which is ever so slightly basic. And when you look at Enbridge's field sampling data, that's in line with the historical values. Why are we talking about pH? Well, the reason is twofold. The first is around the potential change in acidity to the water body from either acid leaching materials within the rock or from the basic composition of the inadvertent return, the drilling fluids. These rocks within the area, as Ray has pointed out, and DNR has not identified, there are not acid leaching rocks in this location. So we didn't really assess that here because it's not a concern. What we did do was run through a number of different calculations associated with a potential change in pH from an inadvertent return, recognizing that an inadvertent return is not a planned event, but it's something that's possible during horizontal directional drilling. So pH in the water column is variable. Again, on the top right, we see it varied from about 3.5 to 9, with an average value of 7.68. And through that historical sampling, we did identify that there were natural changes of 0.23 pH within a single hour. The numeric criteria of the band stipulates that changes should not be any greater than 0.5 within a 24-hour period. So what I wanted to do was take a conservative assessment and say, let's maximize this inadvertent return. Let's put it in a small water body, and let's see what the potential change in pH is. So let me walk you through how I did this calculation. I looked at the drilling fluids in the muds, which, as Joe pointed out, is about 95% water, roughly a little bit less than 5% sodium bentonite, which is essentially clay materials. And then there are two different additives, which can either be a sodium carbonate, which is a pH enhancer, which brings the pH up, or citric acid, which is a pH reducer, bringing that pH down. Both of these additives are approved by Wisconsin DNR. These are actually food additives in some cases, and they're relatively inert. The point of these pH adjusters is because when you have these drilling fluids, the goal is to get a balanced pH between somewhere about 8 to 10. Remember, these drilling fluids are used to lubricate the drill bit, flush the drill cuttings out of that hole, and cool the drill head as it's drilling. The ratio of the additives is about 0.013 by weight, meaning that if you had about 380 liters of water, you're talking about half a kilogram, maybe a pound of additive. And what I wanted to do was calculate the change in pH following this inadvertent return. So what I said is, let's maximize the release volume. So this is not going to be the initial drill. We're going to do the final ream pass, that maximum volume of the hole. We're going to allow the maximum pumping rate of 4 cubic meters per minute, and we're going to maximize the amount of time that happens for. We're going to allow that drilling fluid to enter that water body for 60 minutes, a full hour. Remembering back, Joe said that he's going to have personnel that are going to be monitoring pressures at all points. They're going to have people walking that line, making sure they're not observing any inadvertent return in the waterway or seeing anything on the top side, meaning I'm now giving you a maximum volume and I'm letting it go on for an hour, not the minute or two that you would have observed, the few minutes that would be observed in a real life situation. I'm also going to conservatively assume a maximum pH value of 10, and I'm going to put that into a medium water course with a flow rate of about 1.06 cubic meters per second. We're going to assume that water body has a pH of about 7.5, kind of right on par with that value that you see in the top right. If you assume those well-mixed conditions and ignore the natural capacity of that water to buffer pH changes, which it does have, then you would conservatively anticipate a pH change of about 0.03. Let that sink in. That means that you would go from a pH of about 7.5 up to a pH of about 7.53 over the period of an hour, which is significantly below any numeric criteria of 0.5 within a 24-hour period. Taking into consideration, the HDD activities are all going to take place greater than 2.1 kilometers upstream from the reservation. This pH change is actually likely below the detection limits, even at the release location, let alone kilometers downstream, and it therefore would not be sufficient to shift the aqueous composition of ammonia or ammonium either. What I mean by that, sorry, it's slightly cut off this slide, is that we need to think about nitrogen in the water body, right? Nitrogen can be in the water body as nitrite, nitrate, ammonia, and ammonium. And as the pH of the water increases at a value of about 10, ammonia becomes one of the predominant forms of nitrogen, and that's the thing that causes toxicity. Because the pH change would be so small, about 0.03, a pH change that takes us from 7.53 or 7.5 to 7.53 would not result in any potential change in ammonia toxicity. The next criteria we were looking at was water quality, specifically around bacteria. Bacteria, specifically E. coli, is the concern is around the safety of water for human activities like swimming, shellfishing, and it's around the fecal contamination from colophages from human, pet, and wild animal waste. When we look at this project, it's a construction project. You're bringing excavators in, you're disturbing sediment. You're not introducing any more waste to the systems. So there are no known activities associated with line 5 that would alter the bacteriological water quality, and that criteria should not be exceeded. I mentioned a little bit about total nitrogen in that previous slide, and I kind of want to walk you through a little bit more on that. Total nitrogen is a well-characterized nutrient in the water body. You've got a minimum value of about 0.04 milligrams per liter up to a maximum value of about 5.6. Average value is about 0.74. When Enbridge went out and sampled, their nitrogen measurements were actually quite a bit higher, almost 2 times higher than the average, than the historical sampling. And what we found is that this is probably the case based on 2 or 3 things. The first is the location of the sampling. Remember, we're looking at about 204 wetlands in addition to those perennial waterways. And those wetlands do have a higher potential to have increased nutrients from those stagnant waters. But we also need to think about the timing of the sampling. And a lot of the sampling happened during